Hello all. In this video, we'll be discussing about the Karatsuba algorithm. The Karatsuba algorithm is a fast multiplication algorithm for multiplying large numbers. It was discovered by Anatoly Karatsuba in 1960, and it's a classic example of divide and conquer techniques in computer science. Limitations of traditional multiplication. Traditional multiplication using the standard pen and paper method involves a lot of repeated multiplications and additions, especially when dealing with larger numbers. Time complexity. The traditional method has a time complexity of big O of n power 2, where n is the number of digits in the input numbers. This becomes computationally expensive for very large numbers. Space complexity. The traditional method requires significant memory to store intermediate results and the final product, especially when dealing with large numbers. Efficiency. The time and space complexity of traditional multiplication makes it less efficient for large numbers, leading to slow processing times. Divide and conquer approach. The Karatsuba algorithm uses a divide and conquer strategy to reduce the number of multiplications required. It breaks the original multiplication problem into smaller subproblems, solves these subproblems, and then combines the solution to obtain the final result. First step, divide. The input numbers are divided into smaller parts of equal size. This simplifies the problem and allows for recursive application of the algorithm. Conquer. The smaller subproblems are solved recursively using the same Karatsuba algorithm, ultimately reducing the problem to base cases that can be solved directly. 3. Combine. The solutions to the subproblems are combined to obtain the final result of the original multiplication problem. Karatsuba's insight. The key insight of the Karatsuba algorithm lies in reducing the number of multiplications needed. It cleverly manipulates the multiplication process by performing only 3 multiplications instead of 4, leading to significant speed up. Key principle. The algorithm effectively rewrites the original product in terms of 3 smaller multiplications which are then solved recursively. Efficiency. This reduces the number of multiplications, significantly improves the algorithm's time complexity compared to traditional multiplication. Base case and recursive steps. The Karatsuba algorithm has a base case and a recursive step. The base case handles the multiplication of single digit numbers directly, while the recursive step applies the algorithm to larger numbers by breaking them down into smaller subproblems. Base case. If the input numbers are single digit, they are multiplied directly. Recursive step. If the input numbers are larger, they are divided into smaller parts and the Karatsuba algorithm is recursively applied to these parts. Combine. The results from the recursive calls are combined to obtain the final product of the original multiplication. Optimizing Karatsuba algorithm. While the Karatsuba algorithm is faster than traditional multiplication, it can be further optimized. One common optimization is to switch to traditional multiplication for smaller numbers, as the overhead of recursion can outweigh the benefits of Karatsuba for very small inputs. Optimize, Optimization strategy. Threshold for traditional multiplication. Description. Choosing a size threshold below which traditional multiplication is used, reducing recursion overhead for small numbers. Optimization strategy 2. Memory allocation. Description. Efficiently allocating memory for intermediate results and the final product to reduce memory usage and improve performance. Optimization strategy 3: parallel implementation. Description: exploiting parallelism in the algorithm by performing multiplications concurrently on multiple processors, further reducing execution time. Complexity analysis. The Karatsuba algorithm has a time complexity of big O of n power log 2 of 3, which is significantly better than the big O of n power 2 complexity of traditional multiplication. This makes it more efficient for multiplying very large numbers. Time complexity. The algorithm's time complexity is determined by the number of recursive calls it makes, and it grows logarithmically with the input size. Space complexity. The Karatsuba algorithm uses more memory than traditional multiplication due to the recursive nature of its approach, but it's still efficient for large numbers. Practical applications. The Karatsuba algorithm has found numerous practical applications in various fields where efficient multiplication is crucial, such as cryptography, computer graphics, scientific computing, and more. Cryptography. The algorithm is used in cryptographic operations such as key generation and encryption, where large numbers need to be multiplied securely. Computer graphics. It's applied in computer graphics for tasks such as ray tracing and rendering, which involve performing complex calculations on large matrices. Scientific computing. The algorithm is used in scientific computing for solving equations, simulating physical systems, and analyzing large data sets. Data processing. It's employed in data processing for tasks such as compression and analysis, where efficient multiplication can significantly speed up operations. Advantages and disadvantages. The Karatsuba algorithm has its advantages and disadvantages. It's significantly faster than traditional multiplication for large numbers, but incurs some overhead due to recursion. Advantages: improve time complexity compared to traditional multiplication, especially for large numbers. Disadvantages: increased space complexity due to recursion, and it might not be the most efficient for very small numbers. Conclusion and future directions. The Karatsuba algorithm is a powerful tool for multiplying large numbers efficiently. Its divide and conquer approach has revolutionized how we approach multiplication, and it continues to be a fundamental algorithm in various fields. Impact: the Karatsuba algorithm has significantly impacted various domains from cryptography to scientific computing. Future research. Future research is fast multiplication algorithms focused on further optimizing the Karatsuba algorithm, exploring alternative techniques, and developing algorithms for specific domains.